Welcome back to Calculus 1. In this lecture, we're going to introduce a quantity that's called the derivative, slightly different than the derivative of a function f at a, which was a number. And we're going to interpret the derivative, whatever this thing is, as a certain type of function. All right, so just to kind of briefly review, any place within mathematics, science, especially computer science, you hear the word function, there's something going on about input being transformed to output. Now that was a kind of a basic perspective you saw in your pre-calculus course when you first were introduced to that. And now we're going to build on it with kind of ideas of calculus. Definitely make sure you're comfortable with the limit definition of the derivative of f at a from the previous lecture. We'll be kind of building on that and making a kind of a very small tweak on it. All right, so let's get to where we were with what we defined as the derivative of f, a function, at a, where a is some x coordinate. So this is our first limit definition that we gave, the one that we used a lot. This is the limit as h approaches 0. Hopefully that looks familiar. We've used it in several examples. And at the end of this calculation, every example that we did where f was a function and a was a number, we got at the end of one of these problems a number. That number represents the slope of the tangent line at a. Okay, now I want you to, again, make sure you're comfortable with this limit definition, because we're going to make a very small notational change to this, but it's a huge conceptual change. We're going to replace a with x. We're not doing a limit. We're just replacing notationally a everywhere with the variable x. So basically, we're just swapping out a for x. What effect does that have? Well, we're going to interpret x as our usual independent variable for input. And what we have at the end of one of these calculations, this expression, the difference quotient, involves functions with x in them. F of x here, there's x everywhere. And you can kind of expect when you go through and simplify this, you might have x's left over. When there's typically x's left in an expression, we can generally interpret it as some sort of function. Just thinking again from, let's just say, basic examples from pre-calculus. So the big change is earlier f prime of a, the derivative of f at a, was a number representing the slope of the tangent line. Now this new quantity that we're calling the derivative of f, so the derivative of a function, this is itself a function. F prime of x is not a number generally, but it is a function. And just think, for functions, something goes in as input. So notationally here, we see f prime of x. So our input variable is x, representing a real number. The output for this function is no longer a y coordinate. The derivative as a function gives as output slopes of tangent lines at your x coordinate that you're plugging in. Now, we'll go into detail with that, but we want to go through some examples first, just to get a sense for what this peculiar function called the derivative looks like. All right, and with that, let's get to some examples. They're pretty much exactly like all the examples that we looked at in our previous lecture on the limit definition of the derivative, where we, in that lecture, called it defining the derivative. And again, the algebraic tricks, very similar, just instead of having kind of more numbers everywhere, since a was a number, now we're going to have kind of more algebraic expressions in terms of x. So pretty much it's the same steps as before within the examples in the lecture on defining the derivative, but now a little more algebra. All right, let's move on. As we were talking about algebra here, just to briefly review our algebraic tricks, this new quantity called the derivative of f prime of x as we're writing it, this always gives an indeterminate form when you plug in h is 0. So the thought is we use an algebraic trick, and we have the same 4 algebraic tricks that we've used a lot. All right, let's go ahead and kind of get to a brief review since the algebra gets a little harder here. All right, first, this is our limit definition of what we're calling the derivative of f. We're going to write that notationally as f prime of x. So notationally, f is the function. F prime is the derivative of that function. All right, this is basically, again, the limit of the difference quotient. And before we get to some examples, let's just review the basic steps that go into kind of one of these problems, for at least the simple examples we'll encounter within this lecture and the corresponding homework. Step 1, simplify f of x plus h. That's typically going to be where there's a lot of algebraic simplifying. All right, step 2, we're going to simplify the difference, f of x plus h minus f of x. Big tip, use parentheses around f of x, what you're subtracting. And then a consistency check at the end of this is all surviving terms should contain h. And then your last and final step, divide by h, which is equivalent to multiplying by the reciprocal 1 over h if we're dealing with functions defined as fractions. All right, now you might want to copy these down into your notes, pause the video if needed, since pretty much all the examples we'll be getting to will just be applying these steps and one of our previously mentioned algebraic tricks. So I'll give you a few seconds, and then we'll get to our first example. All right, let's get to example 1. I'd like you to pause the video and give this one a try. This is asking you to find the derivative of this function f of x, x squared minus 4x plus 7, and we're going to rely on our limit definition. That's our only tool available currently to find the derivative, f prime of x. So pause the video and give yourself several minutes, 3-4 minutes for this if you're on top of your algebra and pre-calculus. We'll check in then. All right, let's start going through the steps from what we reviewed about a few minutes ago. So ideally, you had those in your notes, and you're working through this problem by those 3 steps. It's a good way to attack these problems if you feel like your algebra and pre-calculus isn't where it should be for our course. All right, so step 1, we're going to plug in x plus h everywhere. So just be careful. We're going to properly expand x plus h squared. Do not square x and h and then add. That does not become x squared plus h squared. All right, so properly expand or FOIL that. Distribute the -4, and we get these terms. There's no like terms, nothing cancels here. So that's basically it for step 1. All right, we can move on to step 2, the difference, f of x plus h minus f of x. Notice I am myself using that tip of using parentheses around f of x, what we're subtracting. All right, and just to underline them so you see them, those are the individual terms. All the big amount of terms, that's 6 terms, that's f of x plus h. And then in the brackets, just the 3 terms for the function f of x. All right, now you can distribute the minus in front of the brackets or parentheses. That'll change all your signs, and that's likely where if I find that a student made a mistake, it was in missing distributing that negative or dealing with subtraction properly. All right, so that should simplify here. Now we expect our consistency check to be held and valid, where all surviving terms should contain h. And notice, slowly but surely, we can simplify this and cancel some like terms out. The x squareds cancel, the 4x's cancel, and the 7's cancel. All right, notice what you're left with, 2xh plus h squared minus 4h. And that does pass our consistency check. That's just a good thing to keep in mind since it's very easy to make a small algebraic mistake and kind of not even kind of notice it. So this passes the check, which is good. Now, since everything contains h in it, what we can do is, well, factor that out. All right, so we can factor h out from that, and that's basically the end of step 2. There's really nothing more we can do with simplifying this difference. All right, what we can now do is proceed to the last step, forming the difference quotient dividing by h. And you can see the reason why we wanted to factor h out is so that now it cancels with the division by h. All right, and in pre-calculus, this is pretty much as far as you could go where the question was asking you simplify the difference quotient. All right, well, that's pretty much 90% of one of our current calculus problems. The only thing missing from this question up to here, simplifying the difference quotient, is the calculus concept of a limit. So the last step for us is we take a limit for this expression, the difference quotient, as h approaches 0. And at this point, we already eliminated the indeterminate form. That was all the algebraic steps above. So there is no more indeterminate form. So we can evaluate by substituting or plugging in h equals 0. And we get as our limit the derivative as a function, f prime of x. We get that it comes out to 2x minus 4. So for our function f of x equals x squared minus 4x plus 7, the derivative f prime is 2x minus 4. All right, now that is basically it for this first example. Give you a few seconds if needed to pause to kind of check your algebra. All right, when you're ready, we're just going to jump into a follow-up example where the algebra is not any harder, but typically it is. It's actually less work, but it's usually harder since our function in the next example contains a fraction. You learn that in math professor training. You can automatically make any problem harder by incorporating fractions. You also learn later in math professor training, you can make any calculus problem harder by incorporating trig functions. We'll be seeing that within a few lectures, since I know you all love trig functions so much. All right, let's get to example 2. All right, this is the same thing, just with a different function, f of x as 1 over x. And again, I'd like you to pause the video and give yourself an attempt at this. Now, if you came into this course thinking, my algebra skills are awesome, I'm going to ace this course, let's see how you do with this question. Most of the work here is in algebraically simplifying the difference quotient. Pause the video, we'll check in several minutes. All right, are you ready? Did you think your algebra skills are top-notch? Let's find out. Okay, the first step here, plugging in x plus h to our function 1 over x. That's really simple. There's nothing we can do with that fraction, 1 over x plus h. Worth mentioning, a very common mistake, taking that fraction 1 divided by x plus h. That does not split into the two fractions, 1 over x plus 1 over h. Another common algebraic mistake I see by even some of the best calculus students I've encountered. Again, it's your algebra skills that either allow you to excel or hold you back within Calculus 1. All right, so we can jump immediately to step 2, simplifying the difference quotient, or sorry, just the difference, and subtracting these fractions. This is where all the work occurs. Now we have different denominators, so we can just subtract using a common denominator. The LCD here would be x times x plus h. So if you multiply the first fraction by the missing factor x, second fraction multiply and divide by the missing factor x plus h, you get a common denominator, so you can then subtract the numerators. All right, so from here, it's just being careful with parentheses. Again, one of the biggest tips I can advocate. And we just distribute that minus, and then notice within the numerator, the x's cancel out, leaving us with, in the numerator, negative h. That's where the factor of h occurs. So this passes the consistency check. And then our denominator is just x times x plus h. All right, now before we move on to the third and final step, simplifying the difference quotient, notice the difference here is itself a fraction. If we divide this fraction by h, we're going to have a fraction within a fraction, which there's nothing wrong with that, but that's a little more complicated than it needs to be. So instead of dividing by h, it's equivalent for us to multiply by the reciprocal, multiply by 1 over h. And our reason for doing that, I'll just take my time, we're multiplying by 1 over h instead of dividing by h, so that way it's a little easier for us to see that negative h in the numerator from the difference, that's now going to cancel out with that 1 over h factor. So this just makes the algebraic simplification in this last step a little more obvious. All right, now you can cancel those factors of h out, and we're left with a simplified difference quotient. Again, this is all at the level here of a pre-calculus question. We get negative 1 divided by x times x plus h. The last thing that we need for our calculus course is to take a limit as h goes to 0. And that will give us the derivative f prime of x. All right, so here we've eliminated the indeterminate form with the algebraic trick of using a common denominator. So at this point, we can evaluate by substitution or plugging in h equals 0, and we get as our derivative negative 1 divided by x squared. Notice the x squared is coming from x outside of the parentheses, and with h being plugged in as 0, within the parentheses, we have another factor of x. So x times x giving us x squared. All right, so we get as our derivative of the function 1 over x, f prime of x, the derivative here, is negative 1 over x squared. All right, when you're ready, we'll advance. Again, just take time if needed, pause to let the algebra sink in. Most of the work here is in all these computational problems like this, basically applying one of our algebraic tricks. All right, let's kind of get to interpreting this as a function. So we know how to interpret f of x as a function, but how do we interpret f prime of x as a function? Something about input and output. We briefly gave a short answer to that, but we'll go into detail and take our time with it here. Okay, so let's start first with reviewing example 1. If needed, go back through your notes or pause and rewind if needed. We had the function f of x equals x squared minus 4x plus 7. And we calculated within example 1 the derivative f prime as 2x minus 4. That was by using our limit definition of the derivative. All right, well, let's first interpret the function f as a function, which sounds weird, but something about input and output. Now, the most basic interpretation at the level of pre-calculus is for a function like you've been encountering, you plug in an input x representing a number. So let's say we plug in some x value the output for the function f is the y-coordinate. Recall, you plug in an x value, the function gives you the y value out from that. So as a quick example for this function within example 1, let's say we pick x-coordinate 3. What is f of 3? Well, plug that into the function. 3 squared minus 4 times 3 plus 7 is 4. I checked with the calculator before this. So we get the point, the ordered pair, the x comma y, 3 comma 4. The x-coordinate or input is 3. The output or y-coordinate is 4. All right, that's basic. That's all something you should be extremely comfortable with. How do we interpret now the derivative as a function? Now, the notation we've been saying it's f prime of x. So again, we're going to plug in as input x, representing a real number. What does the derivative represent? We could reword this as us asking right now, what is a derivative? Be nice if somebody gave you a few answers to that in a previous lecture. Recall, we gave 3 answers to what is a derivative. We can say it's slope of a tangent line, an instantaneous rate of change, or a limit. The basic answer I want to give, the one that's kind of most general and applicable kind of early on within calculus, we're going to say a derivative represents slope of a tangent line. So for this quantity or function, f prime, we input a real number, x, the x-coordinate. The output is not a y-coordinate. The function f, the regular original function, gives you as output the y-coordinate. The derivative f prime, interpreted as a function, the output of that is the slope of a tangent line at that specific x-coordinate. All right, so that's how we'll give an interpretation to the derivative as a function. We input an x-coordinate, the output to the derivative is the slope of a tangent line. So just as a quick example, let's say we plug in x equals 3, same as the x value we were plugging in a few seconds ago right above. And what we get is f prime of 3. Notice we're using our derivative formula that we calculated with the limit definition. In example 1, we found f prime of x to be 2x minus 4. And if we plug in x equals 3 to that, we get 2 times 3 minus 4, which would be 2. Now, how we give an interpretation to this is we plug in the x-coordinate 3. The output that we get to the derivative, f prime, 2, which is the output that we get here, that's interpreted as the slope of the tangent line at the point with x-coordinate 3. And right above, in the middle of the screen, if the x-coordinate is 3, the corresponding point on the graph is 3, comma 4. So here we get this interpretation for f prime of 3 equaling 2. We can interpret this as the slope of the tangent line at the point 3 comma 4. The slope of that tangent line would be 2. All right. So we'll be revisiting this once we have some more efficient ways to calculate derivatives. The limit definition is fine, but for more complicated functions, what we've been using, the limit definition, is highly inefficient. So there are some shortcuts coming up soon within our course. All right, let's get to another topic. At this point, once we kind of get to the derivative as a function, usually appropriate to introduce pretty much all the standard notation for derivatives that we'll be using throughout the calculus sequence. Now, there's not any more notation that's any more right or wrong than others, just notation that's more standard for mathematics or notation that's more standard for the sciences and engineering. So we'll take a look at all the standard notations here. All right, so again, let's think back to example 1. we had f of x defined as x squared minus 4x plus 7. We used the limit definition of the derivative to calculate f prime of x to be 2x minus 4. That's the end result of example 1. All right, well, we can rewrite our function. Instead of writing it in function notation f of x, we can also write it as y equals. That's usually the more standard notation. Kind of in algebra, we would write a curve in the form y equals some combination or function of x. All right, and if we express our function as y equals instead of f of x equals, we're going to write our derivative to be y prime. And here, for y equals x squared minus 4x plus 7, the limit definition still gives y prime the derivative as 2x minus 4. We're just changing the notation from f prime of x to y prime. All right, these are the two standard notation. It's kind of the most convenient when writing out by hand. The prime notation is pretty short and quick to write, but it's not the only notation for derivatives. Now let's go back to the limit definition for f prime of x, the limit definition of the derivative. All right, and let's kind of reword and repackage some of this notation. All right, now we're going to switch and think instead of our function as f of x, we're going to replace f of x with y pretty much. Now we're going to introduce notation here, so it's easy for me to lose you, my students, going through this. Some of you might be comfortable with it though. Our numerator, recall, that was the slope of the secant line that we started with. The numerator is your change in y values here. Delta y equals y2 minus y1. Now, we're just using the function interpretation. y2 is f of x plus h. y1 is just f of x. The denominator is delta x. Recall, slope is change in y over change in x values. Our denominator then is just delta x. So delta x is h, x2 minus x1, and x2 would be x plus h, x1 is just x. All right, so what's the point of this? We're just layering different notation on. Well, we get a substantially different looking notation for derivatives now. We get what's called Leibniz notation. Leibniz was one of the co-discoverers of calculus, along with Newton. And this is written as dy over dx, which is still the limit definition. We're just replacing h with delta x. And the difference quotient, we're rewriting it as delta y divided by delta x. Your familiar slope formula, change in y values over change in x values. All right, so again, I'm taking my time to let the notation sink in. This is all just slope interpreted as rise over run. Change in y values over change in x values. To transition to calculus, we evaluate and take a limit as those 2 points, the change in x gets small towards 0. All right, so Leibniz notation there, dy over dx, again, is just notation. Let's point out something about this that will be both helpful and possibly confusing later within the calculus sequence. Be careful with interpreting mathematical notation. Delta y over delta x, that is a fraction. In other words, that's your slope formula, change in y values divided by the change in x values. So delta y over delta x, that is a fraction. That is a fraction bar there. And this next part is going to be confusing. Resist the temptation to think of dy over dx as a fraction. Technically, it is not. Dy over dx, notice in the box over there, dy over dx, a derivative, is a limit. Recall that was one of our answers to what is a derivative, a limit. Now, if we want to get technical, which I know we already are, saying that's not a fraction, dy over dx, but I know it looks like a fraction. The fraction bar there is just notation. It is not a fraction. What we can say dy over dx is, it's a limit of a fraction, as we have in the box there for what's called Leibniz notation. Now, this is again both confusing and maybe helpful currently and later on within the calculus sequence. The best I can say is just to be comfortable with mathematical notation. Eventually, later, you'll start to deal with dy over dx as a fraction, but that's not until much, much, much later within the calculus sequence, probably not until you reach Calc 4, differential equations. Some of you might not have even going there, but some of you are. Some of you might even be going the full path all the way through Calc 27. All right, so let's just wrap up this kind of example 1 that we already did and rewrite all the different notations for derivatives. So now we would have in Leibniz notation, dy over dx, the derivative, as 2x minus 4. Again, we're just changing the notation for the derivative. We're not changing the answer that we get. All right, so let's write down all versions. If we have y equals or f of x equals as the function, x squared minus 4x plus 7, we have all kind of 4 here notations for the derivative. F prime of x, y prime, Leibniz notation, dy over dx, and then what's sometimes called differential notation, d over dx, the derivative of, and then f of x within the brackets that tells you what you're taking the derivative of. And this, again, depending on the context, the problem that we're answering, one of these notations might be better than the others. Either way, all 4 of those notations, when y or f of x is x squared minus 4x plus 7, the derivative, no matter how you write it, is, for this example, example 1, 2x minus 4. All right, so that concludes our first part, some computational examples, and then wrapping up now with basically the kind of appropriate time, in my opinion, to get to all the notation for derivatives. Now, this part of our lecture on the derivative as a function is more computationally challenging. Think of example 1 and 2. It was a lot of calculations, basically a lot of algebra. The next part that we'll get to, part 2, is more conceptually challenging. All right, so we'll pick up with that in part 2.